My dear students, today we shall start some examples of compression member design. So the first problem is calculate the value of radius of gyration for a compound column consist of ISHB 250 at the rate 536.6 Newton per meter with one cover plate 300 mm by 20 mm on each flange. Look at this picture. This is the ISHB and this is one plate at the top and another plate at the bottom. Now for ISHB 250 you need some parameter which you can find from handbook 1. This is the handbook and we have to find ISHB 250. You can see there is two type of ISHB 250. One is 51.0 kg per meter and that is 54.7 kg per meter. You can see the weight per meter is in kg. So ISHB 250 at the rate 51 kg per meter and ISHB 250 at the rate 54.7 kg per meter. Now you have to understand which one is given in our question. So this ISHB 250 at the rate 536.6 Newton per meter is nothing but ISHB 250 at the rate 54.7 kg per meter. So in our question this ISHB 250 at the rate 54.7 kg per meter, this is given. Now you can find the cross section area, that is 69.71 centimeter square. The cross section area is 69.71 centimeter square, that is 6971 millimeter square, and thickness of the plate is 9.7 millimeter. Now calculate Ig, that is moment of inertia about ZZ axis for plate. Look at this picture. This is the plate and you have to calculate the Cg about ZZ axis. So the formula is moment of inertia about the axis which is passing through the CG of this plate plus area of the plate multiplied by distance from ZZ axis to the CG of this plate and its square. So Ia is nothing but the moment of inertia about the axis which is passing through the CG of this plate, that is 320 cube by 12, and AP is area 300 by 20 and Y1 is the CG distance from ZZ axis to the center of this plate. So the height of the I section is 250, that means half of the height of the I section is 125 plus CG distance from the bottom of this plate is 10 millimeter. So 125 plus 10 and that is 135 and square. So you can calculate Iz, and for two plate you have to multiply it by 2. So total Iz is equal to 21910 into 10 to the power 4 millimeter square. So total Iz for combined section, I section and two plates, you have to add 21910 into 10 to the power 4, that is for Ig for plate, and 7983.9 into 10 to the power 4, that is Ig for ISHB 250, and the total Ig is 29893.9 into 10 to the power 4 millimeter square. Now the area of built up section is 6971, that is area of the gross area of the ISHB 250 plus area of the plate multiplied by 2 for two plates. The total area is 18971 millimeter square. So radius of gyration is equal to root over Iz by A, and you can find that is 125.52 millimeter. And for IY, that is moment of inertia about y axis 2011.7 into 10 to the power 4 millimeter square. You can find this value from IS handbook. And for plate, that is 20 into 300 cube by 12 and multiply by 2 for 2 plates, and total IY is equal to 11011.7 10 to 10 to the power 4 millimeter square. So for radius of gyration for IY is equal to 76.187 millimeter. Now the next problem is calculate the design compressive load for a station 350 at the rate 710.2 Newton per meter, 3.5 meter high. The column is restrained in direction and position at both ends. It is to be used as an uncased column in a single story building. Use steel of grade Fe410. The stanchion is a member which is actually compression member supporting floor or girder of a building. And for Fe410 grade of steel, Fy is equal to 250 MPa and Fu is equal to 410 MPa. You know that. The partial safety factor for material against yielding, that is 1.1. We are collecting this data from table 5 of IS 800. The column end are restrained in direction, that means rotational movement, and in position, that means translational movement. So K value is 0.65. You can find this K value from table 11 of IS 800. Look at this table. This is table 11 for effective length of prismatic compression member. And the boundary condition is at one end translational and rotational movement, and the other end, that is translational rotational movement, and the boundary condition is, for our case, this. Rotational and translational movement for both ends is fixed. That means the effective length will be 0.65 L. So the 0.65 is the K value. So K value is 0.65. And the L is 3.5 meter high. So the effective length will be 0.65 multiplied by 3.5. Now the properties of ISHB 350 at the rate 710.2 Newton per meter, that is actually ISHB 350 at the rate 72.4 kg per meter. You can find all those parameter. H is equal to 350, BF is equal to 250, and TF is equal to 11.6 millimeter, and TW is equal to 10 millimeter, and gross area is 92.21 centimeter square, and RZ is 146.5 millimeter, and RY is 52.2 millimeter. You can find all those data from from handbook. So this is the table, and in the question, the ISHB 350 at the rate 72.4 kg per meter, this specification is given, and you can see all those data from this table. Now you have to check H by BF and TF. H by BF is equal to 1.4, that is greater than 1.2, and TF is equal to 11.6 millimeter, that is less than 40 millimeter. And you have to go to table 10 in IS 800. This is table 10 for buckling class of cross section, and you can see for the I section, if H by BF is greater than 1.2 and TF is less than 40 millimeter, then about the ZZ axis you have to choose the buckling class A, and about YY axis you have to choose the buckling class B. So along ZZ axis we need the buckling curve A, and about Y axis we need buckling curve B. Now calculate the effective slenderness ratio, that is KL by RY. K is 0.65, L is equal to 3.5 meter, and RY is 52.2 from IS handbook. So slenderness ratio is 43.58. For this slenderness ratio and FOI 250 and for buckling class B, we have to find out the compressive stress from table 9B. This is table 9 for design compressive stress FCD for column buckling class B. You can see the first column indicates the slenderness ratio value, and this row indicates the yield stress Fy. For our case, yield stress is 250, and for slenderness ratio 43.58, you can see this table gives the FCD value for 40 and for 50. Now you have to calculate FCD value for 43.58. That means it will be greater than 194 and it will be less than 206. So collect those data from this table and calculate the value. So for slenderness ratio 40, FCD value is 206 Newton per millimeter square, and for 50, FCD value is 194 Newton per millimeter square from table 9B. And for our case, that is slenderness ratio 43.58, we have to calculate this one 201.7, and you can see the actual calculation in this equation. Now design compressive strength equals area multiplied by stress. Area is 9221 and multiplied by the compressive stress, and this is equal to 1859.87 kilonewton. And again, about ZZ axis, you have to calculate the compressive stress for slenderness ratio 15.53 and for FOI 250 for buckling curve A. This is table 9A for design compressive stress FCD for column buckling class A, and for slenderness ratio 15.53 and for FOI 250, our FCD will be greater than 226 and less than 227. So calculate this value, that is 226.447, and you can see the equation for this calculation. Now calculate design compressive strength, that is area multiplied by stress, that is 2088.06 kilonewton, and the lower value of those two is actually the design compressive strength, that is 1859.87 kilonewton. The next problem is calculate the design compressive load which the member shown in figure can support if the member is of 5.5 meter effective length. Use steel of grade Fe410. Look at this picture. This is the section, 2 channel section with 1 plate. Now for Fe410 grade of steel, Fy is equal to 250 MPa, and for ISMC 400 at the rate 484.6 Newton per meter, this is actually ISMC 400 at the rate 49.4 kg per meter. You have to find out all those parameters: gross area, BF, TF, TW, RZ, G, IZ, IY, CYY from handbook 1. Now this is the handbook 1, and it is providing us all those parameters for ISMC 400. Now calculate the total area of this section, that is 2 channel section plus 1 plate section. The total area is 20586 mm square. Now calculate the neutral axis distance from the top, and the equation is a1x1 plus a2x2 by a1 plus a2. A1 is the area of channel section, and we have 2 channel section, that's why we are multiplying by 2 with 1 area of channel section. And x1 is the distance from the CG of the channel to the topmost fiber of this combined section. That means this is the CG of this ISMC, and from this point to this point is x1. So total this distance is 400. So this point to this point is 200, and this is 16 millimeter. So 200 plus 16, that is x1. 400 by 2, 200 plus 16. And A2 is area of the plate, that is 300 plus 100 plus 100, that means 500 multiplied by 16, so 8000 millimeter square. And x2 is distance from the CG of the plate to the top fiber, that is 16 by 2. And a1 plus a2 is nothing but 2 into 6293 plus 8000. So y1 is equal to 135.168 millimeter. So distance of ZZ axis from the top is 135.168 millimeter. Now calculate Ig, that is moment of inertia about ZZ axis, that is IGC plus ACAY square. IGC is moment of inertia of this channel ISMC about the CG axis, plus area of this channel multiplied by y square. Y square is nothing but distance from the CG of the channel to the ZZ axis, this distance. And IZP is equal to moment of inertia of the plate about the axis which is passing through the CG of this plate only. And AP is the area of the plate, and Y is the distance from the ZZ axis to the CG of this plate. And we have 2 channel section, that's why multiplying by 2. So IZC is equal to 15082.8 into 10 to the power 4 collecting from handbook, and AC is equal to 6293 collecting from handbook, and Y is equal to distance from CG of the channel to the ZZ axis, that is 216 minus 135.168. So this from this point to this point the distance is 216. That means 400 by 2, that is 200 plus 16, 216 minus 135.168. And IZP is equal to BDQ by 12 plus AP is 500 multiplied by 16, and Y is equal to 135.168 minus 8. So AP is Y is this Y is equal to distance from the CG of this plate to the ZZ axis, that means 135.168 minus 8. So total IZ is equal to 51342.82 into 10 to the power 4 millimeter square to the power 4. Now calculate moment of inertia about y axis is equal to 2 into IYC plus ACY square plus IYP. So IYC is equal to 504.8 multiplied by 10 to the power 4 collecting from handbook, and AC is equal to 6293. Now Y is equal to 150 plus 24.2, that is CYY is equal to 24.2 from handbook 1, that is distance from this face to the CG of this channel, and we have to calculate the distance from CG of this channel to the YY axis. So 24.2 plus this distance, this is equal to nothing but 300 by 2. Total distance is 300 and this distance is 300 by 2 plus 24.2. See, this is total Y. And IYP is equal to B dq by 12, 16 into 500 cube by 12. So IY is equal to 55869.22 into 10 to the power 4 millimeter square. Now you have to calculate minimum radius of gyration. Minimum radius of gyration is coming from the minimum value of moment of inertia. So minimum value of moment of inertia is actually Iz. This is the minimum. So minimum radius of gyration will be Iz by A. So Iz by A, root over Iz by A equals 157.92 millimeter. Now effective slenderness ratio is KL by R, and this is small l, that is effective length, and slenderness ratio is 34.82, and TF value is greater than 40 millimeter. So for the channel section, you can see the table 10 of IS 800. You can see for channel section, for any axis you have to choose the curve C. So for design buckling curve, about ZZ axis is C, and for about YY axis also this curve is C. Now calculate the design compressive stress from table 9C. For slenderness ratio 34.82, you can calculate the FCD, that is 204.734. This is table 9C for compressive stress FCD for column buckling class C, and our slenderness ratio value is 34.82. So you have to collect the data from here, that is for slenderness ratio 30 and 40, and for FY 250, that is FCD value is 211 and 198, and you have to calculate for our slenderness ratio value, that is for our slenderness ratio value the FCD is 204.734 Newton per meter square, and you can see the actual formula here. Now the design compressive load is area multiplied by stress. Area is 20586 and stress is 204.734 Newton per meter square. The total load is 4214.65 kilonewton. In the next video, we shall start another design of compression member.